joining today. Before I start presenting the work I've been working on, I will just give a brief introduction about adhesives, what they are, why they are important, and why it is important to work with wood adhesives and try to make improvements in this field. So wood adhesives are substances that are capable of holding two wood substrates together. And on the image, we can see a simplified representation of this, of a bonded joint. It's an adhesive layer between two wood substrates. And adhesives in wood industry are important today because they allow us to use lower quality wood or recycled wood. We can achieve improved properties compared to solid wood in some cases. And also we can achieve larger dimensions compared with the dimensions that we can achieve with one piece of solid wood. And we can use adhesives and apply them between different substrates, different types of wood substrates. For example, if we bond sawn wood, we can produce cross-laminated timber or glued laminated timber. If we bond wood veneers, those are thin layers of wood, we can produce plywood or laminated veneer lumbers. And if we bond particle boards or fiber boards, we can produce, for example, particle boards, oriented strand boards, or fiber boards. And to make all of these products, we need to understand how adhesives work, how wood adhesion is working. So if we go back to the representation of the joint, if we look deeper into this joint in a smaller scale, we can see that it's not simple bond line. So wood is a porous substrate and adhesive can penetrate into the wood. And the strength of the final bond depends on many factors, for example, adhesive properties, wood properties, processing parameters, and service conditions. For example, if you're using them in humid or dry conditions. So there are these are main groups, and then there are different parameters in these groups. And several mechanisms have been proposed to explain wood adhesion and how these adhesives hold wood substrates together. Some of them are represented on the image. We have mechanical interlocking, that because wood is a porous substrate, as I mentioned, adhesive can penetrate into the pores and improve the strength. And also, it can increase the surface area where adhesive and wood come into contact. There can be intermolecular forces, for example, hydrogen bonding, chemical bonds, or electrostatic interactions. And depending on the system that we are using, several mechanisms can be present, depending, for example, on adhesive type or processing parameters that we are using. And all of these, when they are present in the bond line, they can all contribute together to the bond strength. Adhesives are used today because they're used throughout the history. And today, adhesives can be divided based on different parameters. And one classification is on thermosetting and thermoplastic adhesives. Thermosetting adhesives are applied in a lower molecular weight when they apply on wood. And during the bond formation, they cross-link, they polymerize and increase their molecular weight. And those are, for example, formaldehyde-based or isocyanate-based adhesives. Thermoplastic adhesives, they are applied in higher molecular weights, and they do not increase molecular weight during bond formation. And today, most adhesives that are used are formaldehyde-based. Around 95% of adhesives are formaldehyde-based in wood industry. 85% only from urea formaldehyde adhesive. And they're produced in very large amounts. For example, the global consumption of urea formaldehyde adhesive is 11 million tons per year. And these adhesives are used today because they have a very good properties. They are efficient, have fast reactivity, and also they have good property-price ratio. However, they have some disadvantages, and most main disadvantages are that they are coming from limited resources, and also they contain hazardous components. For example, formaldehyde, which is recognized as carcinogenic by the World Health Organization. And adhesives today, most of them, yes, are formaldehyde-based, fossil-based, but in the history, bio-based adhesives have been used before fossil-based adhesives. For example, natural gum or adhesives that are coming from blood or casein. And because of the fast reactivity in 20th century, fossil-based adhesives replaced them. So they're over to the market. And in order to increase sustainability in wood industry, many bio-based resources are again investigated and studied to be used as components in wood adhesives. In this study that I've been working on, we used polysaccharides as components for wood adhesives. And we focus not only on polysaccharides because they're not polysaccharides that are renewable raw materials, but also we focused on polysaccharides that could be obtained as a side stream from another industry. In that case, we can use materials that are already there, existing, but improve utilization of raw materials and also give these materials higher value. We use several types of polysaccharides. One are wood hemicelluloses. So hemicelluloses are present in wood in the cell wall. They are one of the main components in the cell wall besides cellulose and lignin. And in the cell wall, they are positioned between cellulose and lignin because they have functional groups that can interact with both cellulose and lignin. And this binding role of hemicellulose in the cell wall was inspiration for us to use these polysaccharides as component in wood adhesives. We used hemicelluloses that could be obtained from side stream from pulp industry. So pulp industry is using cellulose as a main component, and side stream hemicelluloses are mostly burned for energy recovery now. So we want to use these hemicelluloses as main component. Another polysaccharide is Chitosan. It's a polysaccharide that has amine and N-acetyl groups along the chain. It originates from shrimp shell, and it is obtained as a side stream from food industry. And the last are algae. It's a group of different polymers inside the plant. So we used microalgae, and in this case we used the whole plant. So we did not fractionate the plant to extract one specific polysaccharide, but we used algae as a polysaccharide-rich resource, also containing other polymers. And we used brown algae and beach cast algae. Brown algae that we used are coming from seaweed farms. And these algae can decrease eutrophication or excess of nutrients in the seawater, so they can be beneficial for the environment. Beach cast algae are deposited on beaches, and their collection can also be beneficial for the environment. So as I mentioned, sustainability in wood industry is important, and globally in the society, sustainability is becoming more important. And in 2015, United Nations adopted 17 Sustainable Development Goals in order to overcome these challenges related to sustainability in the society. And the project I've been working on is related to several of these goals. For example, to reduce number of illnesses from hazardous components, achieve sustainable management of natural resources, reduce marine pollution, and promote sustainable management of forest and halt deforestation. And now coming to the thesis and the projects. Thesis is divided in 6 papers, but these papers can be divided or grouped based on the substrates that we used. In the first 3 papers, we used wood veneers and substrates. So these are thin layers of wood, and these were 1.5 millimeter thickness. In these papers, we analyzed the effect of molecular weight of polysaccharides. We prepared fully bio-based adhesive with wood hemicellulose and Chitosan, and also used Chitosan to partially replace vinyl acetate in polyvinyl acetate-based adhesive. In the second group of papers, we used wood particles as a substrate and produced Particleboards. And then we analyzed the effect of the production parameters. We used adhesive from wood hemicellulose and Chitosan similar to paper 2. And also use adhesive with algae and Chitosan. In the first group, when we used veneers, we applied adhesive on the edges of veneers, and we tried to ensure that there is the same solid amount of adhesive on the bond line. Because when we evaporate water, what is the solid substance of adhesive will hold substrates together, and we tried in the same set of data, we try to ensure that this is the constant value. Then we overlap the adhesives, press them under elevated pressure and temperature. After that, we condition them based on the strength that we want to analyze, and I will show later what are conditioning methods. And we test the tensile shear strength. So we try to pull apart samples until they break. And on the image you can see on the right side, you can see how these tests look like. So now, in the first paper, when we analyzed the effect of the molecular weight of hemicelluloses, we used hemicellulose model, hydrolyzed it under acidic conditions to achieve different molecular weights, and then used these fractions with the different molecular weights to prepare adhesives and bond veneers. Okay. As a hemicellulose model, we use locust bingam. It's a galactomannan that originates from a carob tree seeds. And why we use it as a model? There are several reasons. One is that it has similar structure to wood hemicelluloses. It has high molecular weight, over 1 million Dalton, and that was advantage because then we can relatively easily hydrolyze it and change the molecular weight. And also what was very important in the previous studies in our group, when locust bingam was used to bond veneers, it showed promising bonding performance and also water resistance, even though it has only hydroxyl groups as functional groups in its chain. So now coming to the adhesive preparation and bond strength. In the first group of adhesives, we prepared adhesives with 5% solid content. It's very low for adhesives, but because of when we use non-hydrolyzed locust bingam with very high molecular weight, it has very high viscosity and very low concentrations. So we cannot achieve higher solid content for that adhesive higher than 5%. And on the graph, we can see that molecular weight is decreasing with the strength is decreasing with decreasing molecular weight. But as I mentioned before, the strength depends on many factors. And in this case, it also dependent on the viscosity of the adhesives. So when the molecular weight was decreasing, the viscosity was also decreasing. And on the images you can see above the bars, you can see how these adhesives looked like when they were applied on wood veneers before spreading. And lower viscosity allowed for easier application, for easier spreading of veneers, of adhesive over veneers, but it also resulted in overflow of the adhesive from the bond line during pressing. So for example, on this image, you can see that these are veneers that are pressed with low viscosity adhesive, and you can see that there are some adhesive around the bond line after pressing. And we could not control how much of adhesive we lose in the bond line. So we're not analyzing only molecular weight effect, but also the amount of adhesive. And to prevent this, we prepared second set of adhesives with constant high viscosities by changing their solid content. And when we applied these adhesives between veneers, we saw that overflow is limited. So these are the adhesives, these are veneers that are bonded with adhesives that have the same molecular weight, just different solid content and different viscosity. And you can see that there is, in the second image, bottom image, you can see that there is no adhesive around the bond line. And also, microscope images show that there is more adhesive in the bond line, and in the microscope image, adhesive is labeled with pink color. And then when we analyzed bond strength of these veneers, we saw the different trends. So the highest bond strength was not achieved with the highest molecular weight, but it was achieved with an optimum molecular weight. In this case, 530 and 320 kilodalton. So to conclude this, the highest bond strength is achieved with optimum in molecular weight and viscosity because we have sufficient cohesive strength in the bond line, and also molecular weight allows for penetration of adhesive into the wood, which improves the strength. Now the paper second part, when we used wood veneers as substrates, we prepared adhesives with pulpwood hemicelluloses, hardwood hydrolysate, and Chitosan. And we use these components in different ratios. So first, in this graph, you can see on the x-axis are the ratios of components, and they're based on their dry weights, 3:1, 1:1, and 1:3. And we have different strengths. So one is dry strength. That is when samples were conditioned 7 days in standard atmosphere after pressing, and wet strength. After this conditioning, they were immersed in water for 4 days and then tested in the wet state. So if you look first at the dry strength, we can see that hemicellulose alone did not have sufficient strength, but when they were combined with Chitosan, the strength was increased. And the increasement was linearly dependent on the ratio of these components. With more Chitosan, the strength was improved. Wet strength has similar trends, so hemicelluloses did not have strength, and veneers delaminated in water while they're being immersed for 4 days in water. And the strength is again improved with Chitosan, because Chitosan alone has good water resistance. And it's dependent on the amount of Chitosan. This is also, it's important to mention that viscosity here also plays an important role. Adhesives with more Chitosan did have higher strength, but they have much higher viscosity, and it was more difficult to spread them evenly on veneers. And to understand how adhesives hold substrates together, it is useful to understand interactions between components in the adhesive, but also with wood. And it is very difficult to analyze the bond line. For example, to put veneers in the FTIR and see interactions between wood and components. So instead, to understand better the components and interactions, we prepared films from these adhesives in the same ratios as we used for wood bonding. We pressed them at 120 degrees for 2.5 minutes. And in this case, we could see the interactions between components, but also because we have hemicellulose in the system, it can be used as a model for hemicelluloses in wood also. And in the FTIR spectra, here you can see FTIR of films prepared with hemicellulose, Chitosan, and their combination, and also FTIR spectra of Chitosan starting material, powder of Chitosan before making films. If we focus on the region where we can see carbonyl peaks that correspond to carbonyl groups in hemicelluloses, we can see that these carbonyl peaks shifted when we combined it with Chitosan because of the interactions between components. But also, it has been proposed previously that imine bonds could be formed between aldehyde groups at the reducing end of hemicelluloses and amine groups in Chitosan. And in the FTIR, we can see in the hydrolyzed Chitosan films, we can see a peak that is in this region. Unfortunately, it overlaps with the peak that corresponds to the amide bond in the Chitosan. So we cannot, amide group in the Chitosan. So we cannot conclude that this is coming from imine bonds. But to further investigate that, to analyze this, we did the solubility test. So we used films, put them in acetic acid for 24 hours, because both components, both hydrolyzed and Chitosan, are soluble in acetic acid. And then this separate soluble and insoluble fractions. And what we saw is that hemicellulose films prepared with hemicellulose were almost completely soluble. Chitosan had some insoluble fraction, but what was very interesting, when we combined these two components that are soluble separately, they have improved stability. So you can see that insoluble fraction increased. If we look at the FTIR now of these fractions and focus again on the region where imine bonds should appear, we can see that the peak is present in the insoluble part, but not in soluble part. But what is more interesting is that when we look at the peak that corresponds to the carbonyl groups in hemicelluloses, this peak was present both in soluble and insoluble parts of films. So we saw that in using these adhesives for bonding wood, we saw that hemicelluloses alone do not have sufficient dry strength and no water resistance. But when they are combined with Chitosan, they have improved water strength and improved strength and water resistance. And that is because interactions between components contributed to the strength of the final bond. In the third paper, so previous one was fully bio-based adhesive. In this case, it is partially bio-based adhesives. We used Chitosan to partially replace vinyl acetate in polyvinyl acetate adhesives. Polyvinyl acetate is adhesive that is commonly used for wood bonding, and it is prepared by emulsion polymerization. And just briefly about emulsion polymerization. In the reaction mixture, we have solvent, monomer, vinyl acetate in this case, initiator that will start the reaction, and surfactant. Surfactants are molecules that have both hydrophobic and hydrophilic part. And when they're in water, they organize and form micelles, which have hydrophilic parts oriented toward the water and hydrophobic parts inside of the micelle. And in that case, we can polymerize polyvinyl acetate which is not soluble in water, we can still polymerize it in water in this medium. And in that also what we can achieve is adhesives that have high molecular weight and low viscosity, because chains are located in micelles and they're separated from each other. Instead of using surfactant molecules, we can also use polymers as surfactants, but they need to have hydrophobic and hydrophilic parts in their chain. And this is how we used Chitosan in this emulsion polymerization. So Chitosan has amine and N-acetyl groups in a chain. When it is in acidic medium, amine groups are protonated, that gives solubility to the Chitosan. But N-acetyl groups are reducing solubility. And in the Chitosan that we use, there are 15 to 25% of N-acetyl groups, and that is why we could use this polymer as a surfactant in the emulsion polymerization. Also, we used it with dilute acetic acid so we can dissolve Chitosan. We used Chitosan as a surfactant, but also as a grafting site. Initiator that we used, cerium ammonium nitrate, can form radicals along the Chitosan chain, and then polymerization of vinyl acetate will continue from that point. So polyvinyl acetate chains will be attached, grafted to Chitosan. Also, there could be some homopolymer of polyvinyl acetate present in the final mixture. So polymerized vinyl acetate that is not grafted to Chitosan. So first, when we use these adhesives, we prepared adhesives with different formulations. We used Chitosan both with higher and lower molecular weight. Because if we use Chitosan, similar to locust bingham, what we saw before, it has very high viscosity at low concentrations. So by using lower molecular weight Chitosan, we could decrease the viscosity of the adhesives and then change the formulation, increase, for example, the solid content. In the first two graphs, it is a reference adhesive of Chitosan, and we can see that molecular weight did not affect the strength, and these strengths were mainly dependent on the substrate strength, on the strength of the wood substrate. Then, when we use these Chitosan to polymerize in the polymerization of polyvinyl acetate, first we replaced 25% of vinyl acetate with Chitosan, and again we did not see that molecular weight had the high effect on the strength. But because we used low molecular weight Chitosan, we could either increase the solid content of adhesives or increase the Chitosan amount in the adhesives to have more bio-based component in the adhesives and improve the water strength. And what was interesting is that we have 40% of Chitosan, we have full grafting efficiency. So the whole amount of vinyl acetate chains, every vinyl acetate chain was attached to Chitosan. And this led to a better, because they were all grafted, the chain mobility was lower, and it changed the stress transfer in the bond line, which affected the strength, and the strength was higher than even the reference PVAC adhesive. Yes, that is improved strength with full grafting. So to conclude this paper, when we grafted vinyl acetate from Chitosan, it was possible to lower the fossil content to 60%. The wet resistance of polyvinyl acetate was significantly improved because of the Chitosan that was incorporated, and complete grafting improved the bond strength. And now coming to papers where we used projects when we used wood particles as substrates. In the first paper in this group, or the fourth paper in total, we used wood particles and locust bingham as adhesive. And we analyzed how water content and adhesive content affect the strength of the particle boards. So when we prepared particle boards, we first mixed wood particles with adhesive, and this mixture before pressing is called matte. Then we press them on 150 degrees for 15 minutes, and this is an image how these particle boards can look like after pressing. We condition them until they have a constant weight, and then determine the internal bond strength. Similar to veneers, we try to separate to see how strong these boards are. And just as an example, particle boards, very common particle boards that are used for furniture in dry conditions, should have the strength of 0.4 megapascal. In the first set of experiments, we analyze how moisture content affects the strength of the adhesives, and we prepared different boards with different moisture contents. They can be grouped in these three groups, from 10 to 30%, 30%, and about 30% moisture content. So in the first group, when we had low moisture content, boards broke easily after pressing. So you can see in the image, it was very easy to break them even with low force. With moisture content about 30%, the strength of particle boards was, they had strength, it was possible to to analyze the internal bond strength, but the strength was not sufficient. But with the very high moisture content, the boards were strong. And this is hypothesized to be due to hydration of the adhesive or locust bingham. When water content is below 30%, water is present mostly in the cell wall as a bounded water, but when it's about 30%, water is also present in the lumen of a cell wall as a free water, and this water is available for the hydration of locust bingham. And when locust bingham is hydrated more, it has better interaction. It can have better interactions with wood and improve the strength. What is one of the challenges when using very high moisture content is that vapor blistering and delamination can happen because there is a high amount of water present in the boards. Then this water needs to be evaporated. If we do not evaporate and do not leave enough time to vapor to be removed from the boards, we can have blisters, as you can see on the image. So when we release pressure in the hot press, this vapor is strong enough to separate particles from each other. And the boards that I've previously shown are particle boards that were 9 with 7 centimeters, or small lab scale particle boards. But to see how this matte moisture content affects if we press larger boards, we prepared particle boards with around 30 with 30 centimeters dimensions. And first, what we saw is that if we have enough time, if we have the pressing time is long enough, we do not have any blisters or delamination. If we have the same matte moisture content in the boards, then the amount of adhesive did not affect the strength when we increase it from 12 to 18%. And when we have the same adhesive amount, 18% in this case, the internal bond strength was increased with the higher matte moisture content. This corroborated the hypothesis from before that hydration is very important. Also, what I have to mention that in the previous part, when we have the same matte moisture content, this is the difference in the average bond strength is high, but because of a standard deviation, this difference was not statistically significant. So to conclude this part of the project, particle boards with polysaccharide adhesives can be prepared, but matte moisture content is crucial for the hydration of the adhesives and for a bond strength. Larger lab scale particle boards can be prepared using high matte moisture content and without signs of steam blistering or delamination. And in the final two papers, we use hemicellulose Chitosan and algae Chitosan adhesives. I will present them together. When we used hemicellulose Chitosan adhesives, we used again different ratio of these components, and you can see the different ratios in the x-axis. And we pressed them in different temperatures, 150 and 185 degrees. So what we can see is that with more hemicelluloses, what we want, because this is the main component that we want to use, the effect of temperature is not significant, and also the highest strength is achieved with higher amount of hemicelluloses, which was interesting because hemicellulose alone did not give a sufficient strength. The boards broke easily again, but if we have 90% of hemicellulose, around 90% of hemicelluloses and 10% of Chitosan, the strength is much higher. In the algae Chitosan adhesives, we used brown algae and beach cast algae with different in the 80 to 20 ratio of algae Chitosan. And particle boards that were prepared with only algae, they were broke easily after pressing or before testing, similar to hemicelluloses alone. But when Chitosan was used in the adhesive, the strength was much higher, significantly higher. And both, what was important, that internal bond strength did not depend on the type of algae. So both brown algae and beach cast algae have similar strength, which is very important because then we have more material, more algae as raw material. And this project has been done in a collaboration with the seed department at KTH. And it also included the life cycle assessment of these adhesives and particle boards. And what results show is that the production of chitosan has a negative impact on the environment. So chitosan is produced from chitin. Chitin is obtained from a shrimp shell. It has only N-acetyl groups. But then it is partially deacetylated to have amine groups. And this deacetylation step has negative impact on the environment. So in order to prevent this negative impact, we also analyzed if we can use chitin as a part of adhesive, as a component instead of chitosan. So we don't use this deacetylation step that has a very high impact. So first what we can see is that boards that has algae and chitosan, they did not have a sufficient strength. And this is because chitin is not soluble in water or acetic acid that we used. So it was not hydrated enough to have good interactions with algae or with wood. When we added chitosan in the adhesives, the strength was increased. And what showed that chitin is not contributing to the strength, we can see that when adhesives had the same amount of chitosan, for example, 10%, the strength was similar, irrespectively of chitin in the adhesive. So to conclude these two papers, when we used hemicellulose chitosan adhesives for the particle boards, they show promising results, and the highest strength is achieved with more hemicelluloses in the adhesive. And with algae chitosan or chitin adhesives, type of algae did not affect the strength, and chitin was not contributing to the strength of the adhesive or the board when it was added to algae chitosan adhesives. And to conclude the presentation today, when we use polysaccharide-based adhesives, they show promising results, but it's very important to find balance between molecular weight and viscosity, because that can increase the bond strength. Hemicelluloses, together with chitosan, have excellent bond strength and water resistance. When we use chitosan in polyvinyl acetate-based adhesives, we can reduce fossil content at least 60 to 60%, and water resistance of these adhesives is increased. And particle boards with polysaccharide-based adhesives show promising results, but the hydration of polysaccharide is crucial for their strength. For the future work, it would be interesting to optimize these polysaccharide-based adhesives. They show promising results, but for a larger scale application, the formulation needs to be optimized so we can decrease the pressing time. For example, in the particle board production, if you use polysaccharides with lower molecular weights, they are more soluble, so less water is needed for their hydration, which would decrease the pressing time. Also, cross-linking of polysaccharides can increase the strength, especially with hemicelluloses, but it is very important to find bio-based cross-linkers that are effective enough and they have high reactivity. To analyze also long-term properties of these adhesives or these on the final boards. So are they stable and how they are changing after some time? And also end of life of the products. Can we recycle them, reuse them, and also how to dispose them at the end of their life? And of course, I did not do this alone, so I would like to thank my supervisors, Professor Eva Malmström and Dr. Linda Fogelström, for their support and guidance during the past few years. All co-authors and collaborators for their support either with analysis and discussions. Knut and Alice Wallenberg Foundation, Bioinnovation, Vinnova and Research for funding the project, and also industrial partners that were involved in the project. And I would like to thank my colleagues from Fiber and Polymer Technology Department and Division of Coating Technology. And of course, I would like to thank you all for your attention today.